In all fiber optic systems, it is necessary to join two fibers together with low signal losses and reflections. For permanent joints, fibers can be spliced using a high-temperature electric arc to fuse fibers together after a precision core alignment is accomplished. Fiber optic connectors provide non-permanent interfaces to other fibers, transceiver equipment, and cable management products such as patch panels. The ideal optical connector holds the fibers in perfect alignment in 3 axes. This alignment must be maintained over hundreds or even thousands of connect-disconnect cycles to provide stable, repeatable attenuation and reflection characteristics. The most important element of the connector plug is the ferrule, or termini, which provides the precise alignment and centering of the optical fiber. The ferrule depends on the mechanical tolerances of its outside diameter to do this. Keep in mind that in many commercial, industrial, and mil-aero applications, optical connectors have multiple termini, but to simplify the discussion, we will examine single termini connectors. The body of the plug holds the ferrule, the coupling mechanism, and the boot. The body contains either a threaded push-pull or bayonet coupling mechanism that physically mates the plug with a receptacle or adapter and also provides a keying function that allows the connector to mate in only one position. Strain relief of the cable is usually provided by a crimp sleeve, which firmly secures the aramid yarn in the cable to the plug body. Strain relief can also be provided by adhesives that permanently bond the cable buffer materials to the plug body. In connectors with multiple termini, strain relief is provided to multiple fibers depending on the exact cable structure. At the rear of the plug body is the boot, which limits the bend radius of the cable as it enters the plug body. The other critical component is the mating adapter and its internal sleeve that aligns 2 mating ferrules. Like the ferrule, sleeves are most often made from ceramic and can either have a split or solid construction. The alignment sleeve must precisely align 2 precision ferrules by means of the ferrule's outside diameters. This alignment must be done while providing a low friction fit over a wide temperature range. The mechanical tolerances of connector components are of great importance to ensure a high-quality connection with the lowest attenuation and reflection. A suitable alignment of single-mode fibers requires ferrules with the tightest mechanical tolerances, typically between 5 and 10/10,000ths of a millimeter on the outer diameter. It also requires a roundness tolerance of 0.2 microns. These tolerances must be maintained over the lifetime of the connector, which must provide reliable service over hundreds or even thousands of mating cycles. The other critical dimension of the ferrule is the diameter and centering of the hole through which the fiber will be inserted and bonded. If the diameter is too large, there will be room for fiber movement, resulting in poor core-to-core fiber alignment. If the hole diameter is too narrow, the fiber may not fit through it at all. The smaller the diameter of the fiber core, such as in single-mode fiber, the tighter the ferrule inside tolerances must be to ensure perfect fiber alignment in a mated connection. Optical terminations are also critically dependent on fiber tolerances. Manufacturers strive to produce fibers with accurate and consistent sizes. However, manipulating molten glass into a precision optical fiber has always been a challenge. Optical connectors rely on the outside diameter of the fiber to align it in the ferrule, but if fiber tolerances are poor, the optical performance of even the best connector will be inconsistent. The same situation occurs if the core is not precisely centered in the cladding, known as concentricity error. Again, the axis of the fiber core is not coincident with the axis of the ferrule. This will result in core-to-core misalignment of both fibers and high attenuation in the mated connection. Another source of core-to-core misalignment is core ovality. Here the core is less than perfectly round. If the connection is mated in one particular rotational position, attenuation may be acceptable, but if mated in a different rotational position, attenuation may be unacceptable. Today, vast improvements in manufacturing processes have resulted in fiber with very tight tolerances in core, cladding, and coating geometry. When terminating single-mode fiber, it is absolutely critical that the center of the fiber core is coincident with the center of the ferrule or termini. This ensures that the cores of two mated single-mode fibers will properly align, minimizing the disruption of the light passing from one fiber to the other. In fact, a misalignment of only 1 micron causes a 10% loss of the light passing across a mated single-mode connection. Typical single-mode fiber tolerances are 125 plus or minus 0.7 microns for cladding diameter, less than or equal to 0.7% for cladding ovality, and less than or equal to 0.5 microns for core to cladding concentricity. Multimode fibers with their much larger cores require less precision in the fiber and ferrules. Typical multimode fiber tolerances are 125 plus or minus 2 microns for cladding diameter, less than or equal to 1% for cladding ovality, and less than or equal to 1.5 microns for core to cladding concentricity. These tolerances apply to both 50, 125, and 62.5 125 multimode fiber types. Multimode ferrules are specified up to 127.0 microns with a tolerance of plus 4 to 6 microns or minus 0 microns. In connectors with multiple termini, some method of identifying termini must be provided, both to aid in connector assembly and for troubleshooting. Most of these connector types have identifying letters adjacent to the holes where termini are to be inserted.